Welcome all. My name is Suresh, lecturer in EC from Government Polytechnic Bellanpalli. I'm going to teach the subject electronic device and circuits, in which we have successfully completed all the five chapters. Now we are dealing with the sixth chapter. In that also we have completed the some small topics, that is clippers, different types of clippers, classification of clippers, and series and clippers, biased and unbiased, positive and negative clippers. After that, we have seen in the yesterday's class, that is clamper circuits, and in the ending of the yesterday's lesson, we have also discussed different types of clampers, and we have designed some of the clipper and clamper circuits based on the questions. That is, if we given the waveforms, then we have to design the circuit, and vice versa. Now, moving on to the next topic, today's topic, that is tips to today's first topic, a small topic, is tips to design shunt clipping circuits. Use the following tips to design clipping circuits fast. By dealing the problems, we have designed some of the clipping circuits. These are the tips to be followed or to be useful while designing such type of clipper circuits. Just read those steps and follow them while designing the clipping circuits in the laboratory or at your home. Step 1: to clip the positive going wave, connect the diode with its anode at upper side. See, remember this. These are also helpful in dealing with the MCQ questions in the competitive exams or in the interview type of questions. Also, quick revision and quickly assessing the circuits. Right? To clip the positive going wave, it is to remove the positive half cycle or positive portion of the input waveform. Connect the diode with its anode at upper side. So, right, we have for the diode we have two terminals, right? P and N, positive and negative, that is anode and cathode. The anode should be at upper side. For clipping the negative going wave, connect the cathode of the diode at the upper side. Just compare the waveforms. Here in the above also we have one circuit diagram. See, it is a negative clipping circuit with some V reference. Ignore the V reference voltage. Just see, it is negative clipping. In the negative clipping, read the step 1. For clipping the negative going wave, connect the cathode of the diode. Right, we have anode and cathode fired diode. The N is for cathode and P is for anode. P means positive and anode, K for cathode, and it is N. Right, so connect the cathode N terminal of the diode to the upper side. Right, and if it in case of positive going wave, the anode at it upper side. See, this one is a good example here. In this, the P side is connected upper side because we are clipping the positive side. You can remember like that, P positive, P should be connected upper, and negative clipping, it should be connected at upper, negative side. In that way also you can remember. And step 2: note down the clipping level and its polarity. Note down the clipping level and its polarity. Connect a DC source of that voltage with that polarity at upper side. With that polarity of upper same. If you are clipping the positive side, you should connect the positive voltage. If you are clipping the negative side, you should connect the negative AR. If the clipping should be done at +3, connect the 3 volts DC source with positive terminal upper side. Same. And step 3: if similar polarity of the diode and DC source comes near to each other, add zero point 0.6 volts to the DC source voltage. Otherwise, deduct 0.6 volts from the DC source also, because Point 0.6 is the cut-in voltage of a practical diode if it is in case of silicon, right? In the laboratory also we are considering the we are using actually we are using in the real world also the practical diodes. The practical diodes will have a cut-in voltage 0.6 volts. So in the above example also the IN 4001 is a practical diode which have a zero point 0.6 volts of cut-in, and we have used the V reference, that is negative is connected. And how the connection is made, see, the negative terminal of the V reference is connected to the P side. See here, if read the step 3 and observe the above circuit, then we can understand it easily with example, right? If similar polarity of the diode and DC source, that means P to the plus, N to the minus, comes near to each other, add zero point 0.6 volts to the DC source voltage. Otherwise, deduct zero point 0.6 volts from the DC source voltage. Yes, because with the same, oh, this is not happens because if the similar polarity of the diode, that is P, and DC source comes near to each other, then it cannot they we cannot add like that. No, this is not possible. This is wrong. This is vice versa. That means it's reverse of that question. That is, if opposite polarity of the diode and DC source comes near to each other, then add addition of the zero point 0.6 volts. If otherwise, deduct zero point 0.6 volts, because if you can remember in any um, practical applications, when you add these two DC sources, two batteries, right? If you can remember, if in a particular remote or any electronic appliances, if you have to insert two batteries such that both the batteries has to addition, that means the combined power of the DC source has to be used, then you will add, how you will add, if you have the P and it will connect to the N, and if you have the N, then you have to connect to the P, that plus and minus, the opposite polarities has to be combined. And in the KVL also, if you can remember the KVL circuits, right, the voltage sources will be addition of the voltage are same polarities, minus Vm and minus, in from the yesterday's topics also here, right? In this, what we are doing, the plus Vm and minus Vr, how we got this KVL, because the Vm and Vn are in series, and how they are connected, Vm and Vn, this is also some problem, but you can remember from the KVL equations, right? How you will addition the voltage levels, and how you are detect these voltage levels by the polarities, right? So these are the three steps to design a circuit for particular clipping circuits. Step one is for the positive going wave or negative going wave, which is to be clipped depending on that. Then the upper side, or which terminal of the diode has to be connected to the upper side, and the DC source. If the DC source, so if, depending on the which clipping of portion of the input wave, the DC source has to be connected, that is plus 3 volts example. And how the zero point 0.6 volts will be addition or um, subtraction of the DC source depending on the polarity connections, right? These are the tips you can easily design a particular clipping circuits. Please do the examples by yourself, then only you can understand. Just write the steps in a simpler lines so that you can understand, you can remember it easily. Then design a circuit and apply these steps. Then by practicing 5 to 6 problems, you can easily understand and you can easily remember. Now moving on to the next topic, that is define sweep voltage. As the chapter is wave shaping circuits, till now we have seen sinusoidal wave as input and the output is also a sinusoidal but not a pure sinusoidal because of the clipping or addition of DC source in case of clamping circuits. Now we are moving on to the different types of waveforms. Sweep voltage, the voltage which varies linearly with respect to time, is known as sweep voltage. See, in case of sinusoidal wave, the voltage will not vary linearly, right? It is like a inverted parabola in case of peak up to the peak of the positive. Then again, it is a reverse of the inverted parabola. Shapes. It's not a linear. Linear means it should be y is equal to mx. Such formula has to be applied, and you can see the waveforms also. See the linear variation. So such type of voltage curve are called sweep voltage. An important application of such sweep voltage is used in CRO, cathode ray oscilloscope. We use such type of voltages to sweep the electron beam horizontally across the screen, because the variation of the time should be in proportional with the y-axis. Then only the electron beam, whatever the voltage we are going to display it on the display of the CRO, the waveform should be neatly visible and it should be easily calculable, right? The sweep voltage we will use in the CRO to display the waveform. The output, whatever the waveform we are going to display, it should vary linearly with respect to the time axis. Then there will be a beautiful display of the waveform. A time-based generator is an electronic circuit which generates an output voltage or current that varies linearly with time. So the sweep voltage, how it will be generated from a circuit that is time-based generator circuit. Time-based, because the time that whatever the voltage we are getting at the output, it should be vary linearly with respect to time. So the time-based generator is an electronic circuit which generates an output voltage or current that varies linearly with time. In practice, there are two kinds of sweep generators: voltage sweep generators and current sweep generators. The circuits which produce a current which linearly increases with time are called current time based generators. Circuits used to generate a linear variation of voltage with time are called voltage time based generators. Circuits used to generate a linear variation of voltage with time are called voltage time based generators. Now, the next topic in this sweep voltage state the fundamental consideration of sweep waveform. So, which waveform will be considered as a sweep voltage waveform? Observe the figures, both figure 6.10a and 6.10b. In that, from 6.10a, the waveform is linear variation of voltage with respect to time. Only portion, the rising portion of this wave, and there will be a falling portion also. But the falling portion is called restoration time, and whatever the rising portion is called sweep time. And we have the initial value. It does not start from zero, so we have certain initial value. Now see the figure 6.10b. The initial value is there. Again, the sweep time is there, but the restoration time is zero. The restoration time is zero. TR is equal to zero. So we have two types of this waveforms. Figure 6.10a shows a typical form of a time-based voltage. The first figure shows a typical form of a time-based voltage. As shown in figure 6.10a, voltage starting from some initial value, that is, we have some initial value A, right, indicated. Voltage starting from some initial value increases linearly with the time to a maximum value, after which it returns again to its initial value. voltage starting from some initial value increases linearly with time to a maximum value, after which it returns again to its initial value. Sweep time, the period during which voltage increases linearly is called sweep time. As we have seen in this TS, that is sweep time. Voltage increases linearly with respect to time. That portion is called sweep time, and it is denoted by TS. Next is restoration time. Restoration time, the period during which voltage decreases linearly. The period during which voltage decreases linearly is called restoration time, and it is denoted as TR. Denoted as TR. Usually, the restoration time is very less than the sweep time, as we can see from this figures, both the figures. In the first one, 6.10A, we have restoration time which is less than the sweep voltage. From the figure we can see, and this in figure 6.10B, the restoration time becomes 0. Restoration time is 0 in figure 6.10B, and there will be TS time. That's okay. When restoration time tends to 0, we get a waveform as shown in figure. Such a waveform is called sawtooth waveform or ramp waveform. See, the whatever the waveform we are getting with the TR, restoration time is called 0, that is in the figure 6.10b. The waveform is called ramp wave, sawtooth wave. It is in the shape of a saw. It is in the way of a sawtooth. That's in Telugu we call that saw as rampam, rampam pallu, right? And we have the next topic is distinguish between voltage and current time based generation. We have seen that two types of time based generators are there, that is the current or voltage. So what is the difference between them? In the voltage sweep generator, the circuit which produces a voltage which is linearly increases with time is called voltage sweep generator, right? The circuit which produces a voltage which is linearly increases with time is called voltage sweep generator. Now, the current sweep generator, the circuit which produces a current, in which linearly increases with time is called current sweep generators. These circuits use RC circuits for generating sweep voltage. For voltage sweep, we use RC circuits, that is resistor and capacitor circuits, and for current sweep, we use RL circuits, resistor and inductor circuits for generating sweep current. And voltage sweep generators, these are used in CROs, and current sweep generators, these are used in TVs. TV means in TV also we have CRT, cathode ray tube, but in today's LCD and LED, of course, we don't use this type of circuits. But in earlier days, also in some of the houses till today, we are using such large TVs, right? These are CRT tubes, cathode ray tube TVs. It must be constant current source. In case of voltage sweep generators, it must be a constant current source. In other words, if a constant current is maintained through a capacitor, the voltage across a capacitor is a ramp, right? Capacitor formula, some 1 by C integral or IDT, right? It must be constant current. So that is, in other words, if a constant current is maintained through a capacitor, the voltage across a capacitor is a ramp. And in case of current sweep generator, it must be constant voltage source. In other words, if a constant voltage is maintained across an inductor, the current which flows through the inductor is a ramp. So in this both the circuits, RC and RL circuits, there should be a constant current source and there should be a constant voltage source. The output of current or output of voltage across this device will be in ramp shape. small topic, that is errors. What are the different types of errors in a sweep signal? In practice, the signals generated by time based circuits are not perfectly linear. So, these are the practical problems. We may consider an ideal sweep voltage in which the output voltage linearly varies with time. But in case of practical circuits, the signals generated by time based circuits are not perfectly linear. So, additionally, if the signals are linear, they suffer distortion when transmitted through coupling networks. So, the distortion happens to these signals when transmitted through some coupling networks. The deviation of a signal from linearity can be described in terms of three types of errors. The deviation of a signal from linearity can be described in terms of a three types of errors, that is slope or sweep speed error, slope error or sweep speed, displacement error, that is ED, E small d, E small s, because the S has to be a subletter at E. Yes, displacement error ED, transmission error ET. Draw simple voltage time based generator. Next topic, we are moving on to the time based generator, voltage time based generator. Observe the circuit. This is a simple RC circuit, right? Simple RC circuit, and we have voltage source, constant voltage source plus V, that is VCC, can consider as VCC or some DC source. Because of constant DC source, we get constant current, and a switch across this capacitor, and which opens at t is equal to 0, which opens at t is equal to 0 because of the arrow mark. You can see which opens at t is equal to 0. And another end of the capacitor is grounded, and capacitor is a polarized capacitor. It has plus and minus, and the voltage, sweep voltage, we are taking across the capacitor. Sweep voltage we are taking across the capacitor, and this is the, in the right side of this circuit diagram, we have the output Vs versus T graph, 0 to Ts. 0 to Ts, we have a varying signal, varying voltage with respect to time, but not linearly. Right? It is a rising voltage up to Ts, and it also rises to and reaches to the maximum voltage, that is V, and the curve follows some formula, that is V into 1 minus E by e power minus t by RC, and we will see how this waveform is drawn and how that formula will come. Okay, only see the circuit now. Only R and C, resistor and capacitor is there. There is a switch which will open at t is equal to 0, and there is a constant voltage source, and we are taking the output across the capacitor with positive and negative terminals, same as the capacitor. Operation. Explain the operation of this voltage time based generator. Figure shows an exponential sweep circuit. It is not a linear variation because it is exponential, because in the formula V into 1 minus e power, that is exponential power minus t by RC, so it is also exponential sweep circuit. It consists of a resistor, capacitor and switch connected across capacitor, right? It is a resistor, capacitor and switch connected across capacitor. At t is equal to 0, at time t is equal to 0, the switch S is open, switch S is open, and the capacitor charges towards the supply voltage V. Because till now, what is first we construct the circuit, and switch is closed. Switch is closed because of the switch, and and the switch closed means it's a short circuit which will be parallel to the capacitor, so it will bypass the capacitor and flow through the switch, the current. will bypass the capacitor and it goes through the switch up to t is equal to 0. Up to t is equal to 0. That means t is equal to -1, -2. It is for our practical drawing of the waveform only. Generally, the time negative is not it will not be there, but we are considering the practical for the drawing of this practical circuit. Whenever the switch opens, then only the time is equal to 0. We will consider like that. So up to t is equal to 0, then the capacitor is bypassed, so the current will flow through the switch only. Whenever the time is equal to 0, whenever we want to observe the circuit, then the switch opens. Switch open means open circuit, then the current will flow through the capacitor. That means the capacitor charge. Capacitor will charges and it reaches to the maximum. How much it will reaches to the maximum? Because there is a drop in the resistor. The applied voltage, the current flows through the resistor, there will be a drop. Whatever the remaining voltage will be charged to the charged in the capacitor. So in the second point at t is equal to 0, the switch is S is open and the capacitor charges towards the supply voltage V with a time constant RC. With a time constant RC, the voltage across a capacitor at any instant of time. At any instant of time, the voltage across capacitor formula Vc is equal to V into 1 minus e power minus t by RC. This formula can be derived from the voltage across the capacitor with the initial value, some formula initial value minus of initial value minus final value, right? With that formula from in your BW subject, basic electrical subject or network theory subject, you must have derived this formula, right? Everyone, please remember Vc is equal to V into 1 minus e power minus t by RC. This is the rising of the voltage, that is from the 0 to maximum value. We have V as the maximum value minus, so 1 minus e power minus t by or c, where RC is the time constant. The voltage across capacitor at any instant of time is given. The time, if we consider t is equal to 0, time is equal to 0, what is the value? V into 1 minus e power minus 0 by something. Sorry, t is equal to 0 means, so V into 1 minus e power 0. E power 0 means anything power 0 means 1. So 1 minus 1 will be 0. 0 into V means 0 volts. So at t is equal to 0, we have 0 volts. In the graph, initially we have t is equal to 0, that is the 0. And then at Ts, Rc is equal to Ts. So Rc some value, Rc is the time constant. At t is equal to Ts, then we have voltage at Vs. And the final value, if t is equal tends to infinity, t tends to infinity, what happens? E power minus infinity, that is 1 by e power infinity. 1 by infinity means 0. So V into 1 minus 0, it is V, we have V. The final value is in this, it is V volts. You may ask us, but there will be drop across the resistor, that how it will reaches to the voltage, because though there is a drop, as the capacitor charges, the DC source will as time passes, that DC source, because of the drawing of the energy from the DC source, it will decrease the voltage level, and the KVL equation in this loop will satisfy the KVL, right? So it tends to a very long time after that, the voltage, the supply voltage will become 0. So in that case, the resistor, there will be no flow of current through this resistor. So the voltage drop occurs, the resistor also 0, and the capacitor will reaches to the maximum voltage, that is the supplied voltage. The entire voltage will be available across this capacitor. Now the third point, if the switch S is closed after time interval Ts, then the sweep amplitude attain the value Vs. We get the sweep wave because at t is equal to 0 we have opened the switch, but till t is equal to 0 the switch is closed because the capacitor is bypassed and there is no initial value. There is no initial value because in this Vc is equal to V into 1 minus e power minus t by Rc. That formula came with the initial value we consider as 0 because at t is equal to 0, below t is equal to 0 we have bypassed the circuit, then there is no initial charge. At t is equal to 0 we have opened the circuit and the capacitor started charging. After Ts, some storage time Ts, after certain value it reaches to the value Vs. Then if we close the switch, then again the whatever the voltage we applied the source, the current will bypass, and whatever the stored value, that is the Vs, will start discharging through which loop, because we have connected the short circuit across this capacitor, so it will discharge through that capacitor and the short circuit itself. If the switch S is closed after time interval Ts, when the sweep amplitude attain the value Vs, we get the sweep waveform as shown in figure. If we assume switch resistance 0, so this is, if we assume switch resistance at 0, we get a waveform as shown in figure 3.3b. 3.3b, here it is here, because in this, after Vs is reached, it has to be follow this path with whatever the dotted line, and we indicated V into 1 minus e power minus t by Rc. That has to be, that path has to be followed by the voltage across the capacitor, then that is the sweep voltage. But what we have done, after it reaches to the Vs, we close the circuit, we close the switch, then whatever the current flowing because of the DC bias voltage we have applied externally, that will bypass through the bypass through this capacitor and through the, and it will flow through the switch, and whatever the voltage it reaches, Vx voltage, the capacitor stored, that will also discharge through this switch. And if we consider the switch resistance as 0, if we consider the switch resistance as 0, then the restoration time Tr, it is also R into C. There is no resistance in the switch, and 0 into capacitor we have 0, so the restoration time will 0, then it will suddenly reaches to the 0 voltage, the Vs, from Vs to 0, it will be, it will discharge from Vs to 0 within no time. So that's why we have generated this near ramp. It's not a pure ramp or pure sawtooth wave because of this exponential curve. So in the figure 3.3, hence the time interval Tr is 2. Though the switches may be a transistor in a practical circuit. In a practical circuit, the switch can be a transistor. So with that, we have seen the voltage time-based generator. And from the distinguishing of voltage and current, we have used the RC circuit, right? We have used the RC resistor and capacitor circuit. And what we have, it must be constant current source. If a constant current source is maintained through a capacitor, the voltage across the capacitor is ramped. Constant current is maintained because of the applied voltage, external voltage, DC voltage. Because of that, there is a constant current source. Then we have taken the voltage across this capacitor, that is sweep voltage across this capacitor, that is Vs. Now simple current time based generator. Next topic is simple current time based generator. First see the circuit, observe the circuit. We have a external source VCC, and we have VB, voltage across the base and resistor, and there is a transistor. Instead of switch we use the transistor here, and there is inductor and a diode with RD resistance connected in parallel with the inductor. So this the circuit here. The same circuit has done again again in this place. Please draw the circuit. All of you must draw the circuit. I hope you have all drawn this time based generator circuit along with the waveform. Now draw the current time based generator circuit also. Please draw the circuit compulsorily. I will give 2 to 3 minutes to draw. Please draw the circuits. I hope all of you have drawn the circuit. Now moving on to the topic, the operation of the current time based generator. Now see the operation of current time based generator. A simple current sweep circuit is shown in the figure. A transistor Q acts as a switch and switches on or off the inductive load. An inductor L is connected in series with the transistor. A resistor RD in series with the diode D is connected across the inductor L. Right? By looking at the circuit you have drawn, please compare these statements. This is the circuit details. Now the operation. A rectangular wave is applied at the base. See, is called a gating waveform. VB. For VB, we are applying a rectangular waveform. Rectangular waveform in which we don't have the same times for this higher pulse and lower pulse. It has two levels as shown in figure 6.16b. Here it is. Yes, in this 6.16b we have a rectangular waveform. T is equal 0, we have a higher pulse, that is the level is rising, and it is maintained up to T is equal to Ts. Small time is equal to storage time, and after that it is again reaches to the lower level. The lower level keeps the transistor cut off, while upper level drives the transistor into saturation. Yes, we have applied the VB to this transistor base, in which we have the rectangular wafer. Two levels will be there, higher level and lower level. Because of the higher level, the base we have applied to the base, the transistor will be on position, and in the lower level it will be into the off position. This is applied at the base of the transistor Q and it denoted as PB. As the energy is stored in the inductor, that is when the transistor is in saturation, higher level, then it is in, you can consider it as an on stage, and the energy, whatever the energy we have applied, it will be stored in the inductor. When a current is flowing through it, as the energy is stored in the inductor, when a current is flowing through it, some means should be provided to dissipate this energy when the transistor turn off, otherwise it will damage the transistor. To provide a path for it, a diode is shunted across the inductor. Same as with the RC circuit also. In that, the capacitor after reaching to the some Vs value, we have provided a short circuit path to get the voltage discharge, right? So in the inductor also, in the case of inductor also, we have provided a RD and diode path. The cathode of the diode is connected. The second point in the node section, the cathode of the diode is connected to positive terminal of the supply, while anode is connected to the collector. From the figure you can see in the working case one, when the gating waveform is negative, when the gating waveform is negative, that the rectangular we have two levels, right? The lower level is below the uh, x-axis, that is a negative value, and the higher level is above x-axis, we have a positive value. And the gating waveform is negative, making transistor Q off, and the diode is reverse biased because the diode is connected to the P terminal of diode is connected to the Q, right? Because of this negative voltage, the transistor is off, and whatever the voltage we are applying to this base, that will be applied to the P terminal of the diode. So we are giving the negative voltage to P terminal, right? So because of that, the diode is reverse biased, and hence the current flowing through this inductor is 0. When gating waveform is goes positive, it makes the base positive, it makes the transistor Q on. When the transistor is on, the current will increases linearly with time. That is, when the transistor on, it will be the circuit is closed from the plus VCC through the inductor and through the transistor on position, it reaches to the below ground section. So it will be a closed circuit. Right? It will be a closed circuit. So as long as the current increases linearly with the time, the diode is reverse biased and acts as open circuit, because as long as the first transistor becomes on, then the circuit becomes closed. Then the inductor will store the charge. For how much time it will charge? As long as the current increases linearly with time, the diode is reverse biased and acts as open circuit. At t is equal to Ts, after which reaches a certain time, storage time, the sweep ends. As the gating waveform makes the transistor Q cut off, the stored inductive energy. Because we have designed the Ts, the storage value of the time, such that during the linearly storing of this energy in the inductor, that up to Ts it will store the energy. After it reaches to the Ts, the gating waveform is designed such that it will reach the below level. When the Q become off, then what happens? At T is equal to Ts, the sweep ends as the gating waveform makes the transistor Q cut off. The stored inductive energy, whatever the energy we have stored up to Ts, that is equal to half Li square, makes the anode positive. Inductive energy makes the anode positive with respect to the cathode, and the diode conducts. The inductor current then continues to flow through the diode and resistor. So whatever the stored energy will make the diode in forward bias, so diode will conduct, and the RD resistance, which will be used to dissipate the energy whatever it has stored in the inductor. The inductor current when continues to flow through the diode and resistors till it becomes 0. So it will till it will dissipate entire energy. This current decay is exponential in nature. The decay in the current, whatever the is decay in the current is exponential. This decay time constant, take up time constant. It does also a time constant, that is L by R. L by R. In case of RC circuits, previous topic, we have time constant T is equal to RC, R into C. In case of RL circuits, we have time constant, that is L by R. So at T is equal to 0, Ts, you can see the waveform, then only you can understand it well. See, when the gating waveform, assume the gating waveform has negative voltage during the time T is equal less than 0 in the waveform, then the output is 0, and from the section T is equal 0 to T is equal Ts, we have the gating waveform as positive, then the transistor will be on, it is saturation, then the circuit is closed and the current will flow through the inductor, and whatever the stored energy will be linearly increases with the time constant linear increase with the time, then the whatever the stored energy, that is of Li square, and because I is equal to V by L into T, V by L into T, because of that there is a linear increase in the energy. After it reaches to the Ts, then the gating waveform will become negative, then the transistor will be in off state, but the whatever the energy we have stored in this inductor, it will make the diode in conducts, that is diode forward biases. Though that circuit, that small circuit, whatever the portion of this entire circuit, that small circuit that is composed of inductor, resistor and diode will get activated, that is the diode conducts, and whatever the energy we have stored in this inductor will be dissipated through the RD resistors entirely. The total energy will be dissipated through this RD till it becomes zero. That is the exponential decay. The decay of this energy is exponential and it reaches to zero. It reaches to zero. So we have another waveform also we have drawn across this. That is T versus IL. First one is the T versus VB. That is the gating waveform. We have applied to the base of the transistor. That is VB. Second C. Figure C. We have IL versus T. That is current across this inductor with respect to time. Then we have also drawn certain waveform in the figure D, that is VCE versus T. Voltage across, what is this C? Collector and emitter terminal, VCE, and with respect to time. So what happens with respect to this? So we have got certain wave. So at T is equal to Ts, the inductor current attains a maximum value and then starts decaying exponentially. The gating waveform, inductor current waveform and the collector voltage waveform are shown in the figure 3.9 B, C, D respectively. So we have gating waveform, voltage current waveform and collector voltage waveform. The equation for inductor current during this sweep is IL is equal to VCC by L into T, while the equation for the exponential decay, that is IL is equal, small IL is equal to capital IL, that is the maximum value, into e power minus RD into T minus Ts into L, because we are decreasing the exponential decay from a peak value of IL and from the time Ts. We are not started from the zero, that is decay, exponential decay. It is started from Ts, so that's why we have T minus Ts. T minus Ts by L, actually it is T minus Ts by L, because T by time constant should be there, so because of that by L. The waveform of voltage C VC is shown in figure 3.9D. At T is equal to 0, when transistor is on, the voltage VC is VCC. So in the figure D, see the voltage across the CE, capacitor, so collector to emitter voltage at T is equal to 0, the gating waveform, T is equal to 0, the gating waveform, it becomes the VCC. Similarly, sometime after T is equal to Ts, see, please read it as Ts, not the ST. The VCE, this is the VCE, is VCC. The VCE is VCC when transistor is off. When transistor is on, VC is the saturation voltage across Q, which is very much small. At the instant when the transistor becomes off, a spike of the amplitude, that is IL or D, appears across L. The spike should be less than the collector base breakdown voltage. The spike also decays with some time constant, same time constant as that of the inductor current. It can also be observed that the spike duration depends on the inductor L, while amplitude of spike does not depend on L. See, in the waveform we have a spike at T is equal to Ts. At T is equal to 0, we have a spike which is IL into RD. The spike value should be selected such that uh, spike value should be such that it should not break down we should not break down this transistor. So with this we have completed today's topic, that is time based generator, and that is voltage time based generator and current time based generator. And we have seen the sweep voltage definition, right? So we'll meet in next class. So please, if you have any doubts, please mail me at sureshakul2001@gmail.com. So now I am closing today's session. Thank you. Thank you one and all.